Hi there, Mr. Sutton here, bringing you the BC Calculus 8-6 Extra Practice Number 3 solutions on polar functions advanced area. On this problem, I want to find the area enclosed by the 8-petaled rows, r equals 2 sine of 4 theta. Let me graph this out since this is a grapher problem. So to graph this out in mode, I went down here and changed it from func to polar mode. Just so I can graph things the way they're supposed to be graphed with these polar coordinates. And now if you go to y equals, you no longer have y equals. You instead have r equals, where I've put my r function in here from the problem. And just to make my life even easier, and it's just because it's kind of cool, I'm going to go over here and I'm going to change this little line to, I'm going to press enter twice, 1, 2, and it now changes into kind of a line with a ball at the end of it. This is going to tell me where my function is going as I move through the different angles and graph this out. So let me also go to window, and it looks like I'm graphing this from 0 to 2 pi, which is good. That's what I wanted. Let me do zoom 0 now, zoom fit, and see what this rose looks like. So we're drawing this flower. There we go. We're going all over the place. And boy, I couldn't even keep track of where that thing went. It keeps coming in and out of the origin. So that's kind of confusing. There's a picture. We want to find the area in all of these petals. Part of the issue, if you just try to use your standard area formula and go from 0 to 2 pi, you're going to have a negative radius along with positive radius in there. So some of those might cancel out and not give you the true area. A safer strategy on this would be to find the area of one petal and multiply that by 8. So just taking a look here, I'm going to do zoom 0 again to regraph this, because I want to see kind of what draws this first petal, how soon this first one gets drawn. So let me do zoom 0 one more time, regraph that, and it looks like the very first thing we do is draw that first petal. So I think this first petal is going to be the safest one to use. So to figure out the limits of integration for this first petal, I'm just going to figure out where the r value first equals 0, so set this thing equal to 0 and solve for theta. So if I divide both sides by 2, that's just going to give me sine of 4 theta equals 0. And then if I basically figure out where sine of an angle is 0, that's where the y value on the unit circle is 0. That happens at 0, pi, 2 pi, 3 pi, every multiple of pi basically, every integral multiple of pi. So we can say then that 4 pi equals 0, pi, 2 pi, all of those. So the first two values, if I divide by 4 to get theta, are just going to be 0 and pi over 4. So our first petal's limits, we're going from 0 to pi over 4 for the angles. So we're going to have 8, by the way, we're going to have 8 of these areas here. So my overall area, I'm going to have 8 times the integral from 0 to pi over 4 of, and now just using my area formula, it's normally 1/2 r squared d theta. So in this case, that's going to be 1/2 times this stuff squared d theta. And now let me do all of that on the calculator. So here's my lovely rose again. Let me clear that out. And instead of doing 8 times integral 1/2, I'm going to pull this 1/2 out here to be with the 8 and basically get a 4 outside. Save myself a little bit of stuff, and then let me do math 9 for integral. We're going 0 to pi over 4. And then inside now I'm basically just going to be doing 2 sine of 4 theta squared. But hold on a sec. I actually stored this as R1 when I graphed this whole thing out. So I'm going to do alpha trace and just pull up y1 here. All I have to do now is square that. Go over here, I'll put an x or a theta in there, whatever this input variable is. Press enter, and that comes out to 6.283. For this problem, I want to find the area shared by these two cardioids. So let me go on my grapher and see what I'm looking at. So on my grapher in mode, I've changed from function mode to polar mode right here. And now my y equals is an r equals, where I've entered these two polar functions. I'm going to go ahead and graph these. First, I'm going to change these lines over here, though, by pressing enter twice. and changing them to lines with balls at the end. That's just going to help me trace out where this function is going. My window, I'm just making sure it's from 0 to 2 pi. This is good. Let me do zoom 0 now, zoom fit. So this is the 1 plus cosine one right here, going from here this way. So we get a cardioid over there. It's the rightmost cardioid. And starting here, this is now going to be the 1 minus cosine piece of it. So there we are. Now these are kind of going all over the place. I'm just going to play it safe. And my strategy is I'm just going to find one of these little sliver areas here and multiply that by 4. So I'm going to multiply half of one of these shared loops by 4. And I think I want to use just this one here in the first quadrant. So we saw that that was formed in the very beginning by this 2 parentheses 1 minus cosine of theta function. So I just want to do that one between 0 and pi over 2. So now my area formula I'm going to use, in general we have the integral from a to b of 1/2 r squared d theta. So I'm going to do 4 times, and now the area formula, integral from 0 to pi over 2 of this one right here. So I'll square this whole thing and put a d theta next to it. And actually I have to multiply it by 1/2 as well. So 1/2 times all this squared d theta. And be careful, it's tempting to multiply the 1/2 and the 2 together and cancel those out, but the 2 is being squared along with everything else. So I'm really just going to write it out like this. And now I'm just going to do this on the calculator. So here's what I've got written in so far. I'm not quite done, but I've got a 4. I did a Math 9 integral 0 to pi over 2. And inside here from my integrand, I've got 1/2, and now I'm about to do all this stuff squared. Now, just to save myself a little bit of time, I did store all this stuff as R2 when I graphed these things out in the beginning. So as a shortcut, I can do alpha trace, pull up my R menu, and I'll just select R2 from all that. And don't forget to actually square that. And now let me just go over here, put in my input variable, D whatever, and then enter to get 850 if I round that to 3 decimals. There we go. For this calculator-based free response problem, we have the graphs of the polar curves r equals 3, which is this circle here with a radius of 3, and r equals 4 minus 2 sine of theta, which is this thing that's not a circle, this cardioid, I guess. And we're told that these curves intersect at pi over 6 and 5 pi over 6, which we definitely could have found on a calculator on our own, but it's nice of them to give us that. So our first task is to find the shaded region between these. And in order to do that, so in general, I have my area formula. Area equals the integral from a to b of 1/2 r squared d theta. But that area formula by itself doesn't quite cover what's going on here, because you have 2 different curves that you have to take into account as we go. So if you take a look at between pi over 6 and 5 pi over 6, you're adding up kind of these radius strips, which are distances from the origin to the curve. And these are, along this interval, you're going from the origin to that cardioid curve right there. But everywhere else, you're going from the origin to the circle and adding up those radius strips. So you're really going to need 2 different integrals. One that covers this little stretch between pi over 6 and 5 pi over 6, and another covering this stretch that you're basically going to the circle. Let me take care of the circle first. That's the harder of the 2. But I mean, the circle looks like a nicer formula, but it's actually a little trickier to get this area. So I need for my circle to go from 5 pi over 6 right here all the way around to this spot. Now I say this spot. You're probably thinking, well, hold on, isn't that just pi over 6 right there? Well, yeah, it is if you're starting at 0 and going there. But if you're starting all the way over here at 5 pi over 6 and going all the way around the circle and coming back here, this is no longer, at least as far as your calculator is concerned, pi over 6. This is 2 pi plus pi over 6, which is 13 pi over 6. So when I'm doing my area formula, I'm going to need the integral from 5 pi over 6 to 13 pi over 6. And now I'm doing 1/2 r squared d theta. In this case, we're going to then do 1/2 3 squared d theta, because that's the circle. So we're doing the circle from 5 pi over 6 to 13 pi over 6. That gives me all of this area along that interval. But now, wait a sec, I still need the area between pi over 6 and 5 pi over 6. So I'm going to add the integral along that interval. And now I'm going to be using 1/2 times this r that they gave me, 4 minus 2 sine of theta, quantity squared. So I've got the circle and I've got the cardioid, and now I'm just going to add all this up on my calculator. So here's what I've got so far. This is just the first of these two integrals. I did Math 9. I've got my integral from pi over 6 to 13 pi over 6, 1/2, 3 squared. And I'm using just regular functions, so I'm going to use x for my input there, even though it says theta down here. And now I'm going to, off camera, enter in this other interval, this other integral. But wait, before I do that, I just noticed that I had pi over 6 there. I needed 5 pi over 6. My calculator was covering up that crucial 5 in there. Okay, problem fixed. Now let me enter this other interval. So doing this, I've got plus the integral from pi over 6 to 5 pi over 6. We have 1/2 4 minus 2 sine of theta. Close the parentheses, square that, dx. Press enter, and all that comes out to 24.709. For this part of the problem, we have a particle moving along the polar curve r equals 4 minus 2 sine of theta, so that's that cardioid curve there, so that at time t seconds, theta equals t squared. Well, that's interesting. We want to find the time in the interval between 1 and 2, at which the x-coordinate of the particle's position is -1. So basically, we need a way of expressing this polar curve in terms of x. I have the general formula x equals r times the cosine of theta. So applying that here, I can say that x equals 4 minus 2 sine of theta times cosine of theta. But hold on a sec. They said that theta is really t squared in this situation. So I'm going to write out parentheses 4 minus 2 sine of t squared, close parentheses, times cosine of t squared. So we have an r and we have a theta replaced by t squared. Now we wanted to figure out the time at which all this x value here equals -1. So set it equal to -1, just like I did there, and now we're just going to solve this on the calculator. So to do this on the calculator, I'm essentially going to enter the left and the right half of my equations as y equals. And I'm going to be a little bit more clever even about this. Because I kind of looked ahead on this free response, and I know that I'm going to need this r piece, this 4 minus 2 sine of t squared piece, to also write out the y coordinate at some point. I'm just going to enter this whole r piece as y1. And then to create this actual left side of the equation, which represents x, I'm going to go down to y2, and I'm just going to do alpha trace y1 times cosine of x squared. So because I've got this r piece here as its own y1, I can reuse it somewhere else as well without having to rewrite it, just saving a little bit of time down the road. Okay, so I've got my my left side of the equation, and I'm going to deselect r, y1, because I don't want to actually ever graph that in this. So this is the left side of the equation I'm graphing, and now back in r3, I'm going to put -1, because that's the right side of the equation. And what window should I use? Well, they said the time between 1 and 2. So let's go ahead in my window, and I'm going to go from a 1 for my x min to 2 for my x max. And let's do zoom 0, zoom fit to see where these intersect. So there is the left half of my equation, that crazy sine cosine combo sort of curve. And here is the line -1. So we want to figure out what intersection point that is. So let me do second trace, option 5, for intersect, and then press enter 1, 2, 3 times to get 1.428. And that's also going to be, let's see, that's going to be seconds because that's a t value. For the last part of this problem, for the particle described in part B, and the big part of the description was that theta is really t squared, we want to find the position vector in terms of t. So I have an x and a y value for this. X of t we kind of wrote back in part B. We said that that was going to be r times cosine of theta, but again, theta is replaced by t squared. So we have 4 minus 2 sine of t squared times cosine of t squared. So that was x of t. And now for y of t, we're doing pretty much the same thing. So we're going to have again the r value, so 4 minus 2 sine of t squared. But this time we're going to multiply by sine of t squared, because it's r sine of theta to get the y value when you're going from polar to rectangular coordinates. Great. So just to make sure that they really understand what I just did here, I'm going to write position vector equals x of t comma y of t. And now there's no ambiguity. This is my position vector in terms of t, which is what they asked for. Next, they want us to find the velocity vector at time 1.5. So I essentially need to find the derivative of x of t and y of t, so x prime of t and y prime of t, and plug in 1.5 to those. So then my velocity vector is going to be x prime of 1.5 comma y prime of 1.5. Now, one way to do this would be to actually figure out algebraically what x prime and y prime look like. And this is going to be kind of nasty and crazy. This is a product rule involving chain rules and just a big mess. But since you've already defined what x of t and y of t are, you're actually allowed to just take the derivatives of those functions on your calculator at a single value, namely 1.5, without showing what it looks like as a formula. So that's what I'm going to do. I'm just going to plug all this in to my calculator using the derivative function, and I'll just write the final decimal answers that I get from that. To minimize my chances of making mistakes on this, I'm going to do a little bit more work in my y equals now. So back in part B, I did, let's see, y1 cosine of x squared. That's basically x of t. We have that r function with a t squared in there times cosine of t squared. So that's in y2. And I'm not going to bother erasing y3, just leave it in there. But now I want to do y of t. I'm going to put that in y4. So that's going to be r times the sine of t squared. Again, r was stored as my y1, so I'm going to do alpha trace y1. And now I'm just going to do sine of x squared. So there we go. I've got y2 is x of t, and y4 is y of t. Quitting out of there, I'm going to take the derivative of x at 1.5, so math 8 dx, and I'm going to do alpha trace y2 because that's where I stored x of t, and we're doing that at 1.5. Pressing enter, I get a value of about negative 8.072. So I'll put that in my velocity vector. And now for the y prime of 1.5, I'm just going to yank my input from right before. And the only thing that's going to change, I'm still taking a derivative, but now I want the derivative of y. So I'm going to change y2 to alpha trace y4 because that's where I ended up putting in y of t. Still evaluating at 1.5. Press enter, and that comes out to negative 1.673. So there's our velocity vector. For this no calculator free response problem, we have a figure with a couple circles in it. This big circle here at the origin is x squared plus y squared equals 2. And this shifted circle, this is the x minus 1 squared plus y squared equals 1 circle. And they're telling us these circles intersect at 1, 1 and 1, negative 1. R is the shaded region in here. We're going to be working with R now in the first part of this problem. We want to set up an expression involving one or more integrals with respect to x that represents the area of R. Okay, well, if I want to have integrals with respect to x, dx's, that means that I need to have these functions expressed as y equals something in terms of x. So I'm basically going to treat the area here as bounded by some semicircles and the x-axis. That's really what's going on here. So let me rewrite this first one. I'm going to subtract x squared from both sides. And then to get y by itself, I have to square root both sides. Now, normally you get a plus or minus, but obviously you don't want y equaling two different things. One thing is enough. So do I need the positive or the negative root? Well, since I want the top half of this circle here, I want the positive root. So I'm going to write this as y equals positive radical 2 minus x squared. And I'm going to call that y sub a of x. So again, that's the semicircle, the top half of the big circle here. Now I need to also talk about the top half of this smaller shifted circle. So I'm going to rearrange this equation here. I'll subtract x minus 1 squared from both sides. And then I'll just square root both sides there. And again, I'm going to take the positive root because I want the top half semicircle. So we have the square root of 1 minus x minus 1 quantity squared. And I'm going to call all that y sub b of x because I really don't feel like rewriting that ever again. Okay, so now I need to start thinking about getting this area. If I'm integrating with respect to x, I'm basically going from left to right, and I have this concept of a top function minus a bottom function. Since the bottom function is just the x-axis, which is just y equals 0, really I'm just thinking about what this top bounding curve is. And the problem here is that this changes. Between 0 and 1, you're using the semicircle from this shifted circle here, y sub b of x. But from 1 until this spot where the big circle's hitting the x-axis, you're using the semicircle from that big circle, y sub a. So in order to really write all these integrals out, I'm going to need to know what this intersection spot is right here. So let me find that by taking y sub a and setting that equal to 0, just to see where it crosses the x-axis. So if I square both sides here, and then let's see here, add over x squared, square root both sides, I get plus or minus radical 2. And really, positive radical 2 is all I care about. I don't really care about anything over on the left side here. But at least I know now that's going to be radical 2. So to get my area then, I have one integral. Limits of integration will be 0 to 1. And that's going to be the integral of y sub b, the smaller semicircle. So y sub b of x dx. Plus, now I have an integral from 1 to radical 2 involving that second semicircle, y sub a of x dx. And this is an expression that represents the area of R. For this next piece of the problem, they want us to set up an expression with one or more integrals with respect to y, representing the area of R. Okay, so now we can't think about this as top minus bottom anymore. Now we have to think about this as right function minus left function, and we're going to be going from bottom to top. So at least our limits of integration aren't so bad. We're going from 0 for the y value here to a y value of 1 up here. So that's good news. More good news, there's only one right function and one left function. So if I'm doing right minus left, I'm just going to need a single integral from 0 to 1 to do this. But here's the tricky part. Now we have to express these circles as semicircle functions of y, because we have dy now. We want to integrate with respect to y. So I'm going to rearrange these now and write these as x equals something with a y in it. So let's start with my big circle centered at the origin. So I'm going to write x squared equals 2 minus y squared this time around. And just like before, I'm going to have to take a square root. But I have to pick between the positive and the negative root. Now, just looking at what part of the circle I need, I want the right half of this circle because I need this piece right in here. That's going to be like my right part of that bounded region. So because I want the right side, I need the positive root here. So x equals a positive root. So we'll call x the positive root of 2 minus y squared. And I'm going to call this x sub a of y, so I don't have to write all this out again. Next, I have to rearrange this other one. So I've got 1 minus y squared there. And just like before, I'm going to have to take a square root. And then after I take the square root, I'm going to have to add this 1. But let me decide if I'm doing a positive or a negative root for this smaller circle. Now, for this smaller circle, I want the left half of that circle, because I need this little piece in here between 0 and 1. So to get that piece, I need the left side. Because I want the left half, I need the negative root. So I'm going to write that x equals negative radical 1 minus y squared. But then don't forget you have to also add this 1 in here to get x truly by itself. So all of that negative radical plus 1, and I'm going to call that x sub b of y. So now for my integral, my area, I'm going to have the integral from y equals 0 to y equals 1. And I don't have to write y equals because I'm going to put a dy later. But these are actually y values now, not x values. And I'm doing right minus left. So the right piece of this right here, that was x sub a. The left piece was x sub b. So I'm going to write x sub b of y, or x sub a of y rather. So x sub a of y minus x sub b of y. Just like that. Dy. And that's now an expression integrating with respect to y for that area. For the last part of this problem, kind of following suit with what we did in the first two parts, first we had to do integral with respect to x to find the area. For part B, we had to do y integral to find the area. Now we need a polar integral, polar area version of the area of R. So now they're telling us that the polar equations of these circles here, and they're finally giving us the equations. We've got r equals radical 2. That's this circle here with a radius of radical 2. And then r equals 2 cosine of theta. That's this other circle. And I'm actually going to relabel those. I'm going to call this first one here r sub a and of theta, and I'll call this other circle here r sub b of theta. So we want to set up an equation, of course, for the area here. Now, the way that we do this with polar coordinates, your area formula in general is the integral from a to b, which are both angles, of 1/2 r squared d theta. So these are the r's that are going to be squaring inside those area formulas, but we need to find limits of integration. So we have to think of this in terms of kind of radius strips coming out from the origin to the edge of the bounded region. And this is a little bit tricky because you're starting at an angle of 0 and you're getting radius strips going out to this r equals radical 2 function, r sub a. But then once you get to this intersection point, your radius strips are no longer going out to that big circle. They're going out to this smaller circle, this 2 cosine of theta function. So I have to figure out what this angle of intersection is here, because that's where I'm going to change from one integral to another, because I'm using radius strips to a different bounding function. So I need to figure out what r sub a and r sub b equal each other. Well, that's going to happen at the point 1, 1. They told us the circles intersect at 1, 1. So what's the angle there? Well, to find an angle given a point, I just need arctan of y over x. So in this case, we have arctan of 1 over 1. And the arctan of 1, you might remember, that's going to be pi over 4. So that's where our integrals are going to switch over. So I'm going to have one integral going from 0 to pi over 4. And for that integral, I'm using the r sub a function, that big circle. So we're just going to write 1/2 times r sub a of theta squared, d theta. And now I have to add another integral. We have to have the other integral take over at pi over 4. So going from pi over 4 all the way to pi over 2 here. And that's going to be 1/2 r sub b squared, or r sub b of theta squared, d theta. And there's our expression for the polar area version of this area R.